During development, the scripts in our games are going to get more complex, and that's why it's so important that our code is organized, easy to understand, and expandable. Today, we're going to do something incredibly important when programming our games to achieve and maintain these characteristics. We are going to refactor our current character controller script by implementing a hierarchical state machine, state factory, and rename some of our current variables for proper naming conventions. Of course, you can grab access to this project's files over on patreon.com/iHeartGameDev while supporting the channel. But now, let's get started. As a quick refresher, in the previous videos of this series, we learned to make our character move and jump. We did so by adding the built-in character controller component to our Jammo character model that's free to use from the hit YouTube channel Mix and Jam. We added animations to Jammo and integrated Unity's new input system to monitor the player's input on both keyboard and controller. In our code, which is where we will be spending the majority of this tutorial, we set up callback functions to handle each of the player's inputs that we set with the new input system. The callbacks update variables that we use to control Jammo's movement, and transition between its animations in additional functions that are appropriately titled handle animation, handle rotation, and within the update function. For jumping specifically, we attempted to replicate Mario's jump by creating 3 different jump heights and jump durations that are set when our character is first instantiated into the game. The handle jump function is called when the player first presses the jump button, and handle gravity is always being called in update to constantly enforce gravity on Jammo. If you really want to understand all of this code, I highly suggest checking out the previous videos and learning from there. But we are at least now on the same page of what each function generally does and have a firm overview of the project. So this is our starting code, and by the end of this video, it'll be broken down into a hierarchical state machine, and we'll have a solid understanding of the fundamentals behind that. To begin this code refactor, let's talk a little bit about C# naming conventions. Variables in C# are typically written in camel case or Pascal case. Camel case is when the first letter of the variable is lowercase and any preceding words within the variable have their first letter capitalized. Pascal case is just like camel case except the first letter is capitalized. Now, when do we use each when programming in Unity? We'll notice that when generating a new script from within the Unity editor, the auto-generated class name is Pascal case. That is to say, classes in C# are typically written using Pascal case. We'll also notice that auto-generated start and update variables are also capitalized. This is because methods and functions are written using Pascal casing as well. Now, let's say we have an example function and it takes a parameter. The class type of the parameter, as we know, will remain Pascal case, but the parameter itself will be camel case. And if we were to create a variable local to this function, it would also be camel case. The same can only sometimes be said to the class's local variables, otherwise known as member variables. If a member variable has the public or protected access type, it is typically Pascal case. However, private member variables are denoted by an underscore and then camel cased. If we want to get more specific, an older method would prefix an M prior to the underscore. This prefix is lifted from what's known as Hungarian notation, so go ahead and check that out if you are interested in learning more. And a couple noteworthy specifics include static variables always being written at the top of the class, interface declaration prefixes a capital I to a Pascal written name, and enums are also written using Pascal casing. Cool. Opening up our current animation and movement controller with jumping script, we'll now use this knowledge to refactor the script's variables. Most noteworthy is that we'll be adding underscores to the member variables. And already, we can see that in the script's functions, we can more easily tell the difference between variables defined in the scope of the class versus variables local to the function. Wonderful. Okay, so what is actually wrong with our current script? As we can see, it clearly works and is written using relatively understandable functions. However, the logic is already growing to be a little more complex than it should be, and there's not even that much going on. Jammo can move and jump. There is no crouching, swimming, dodging, wall running, none of that. If we were to add all of this functionality for Jammo in this single script, not only would it get much bigger, but it would get so much more complex because we would need to add extra conditions so that the new logic wouldn't interfere with the old logic and vice versa. On top of that, all of the conditional logic would always be running with every single update, which could lead to performance issues. So what do we do? If we remember from the explanation of state machines in the original state machines tutorial on this channel, we can solve this massive script problem by essentially splitting the logic into smaller chunks called states. Each state will contain the functionality only relevant to that given state. For example, in a running state, we'll have logic that controls Jammo's movement speed. Jammo will then switch between each of the states that we've defined so that only one state and its associated logic is active at a given time. Clean, efficient, and understandable. However, in this tutorial, we're going to take state machines to the next level with a hierarchical state machine. In a hierarchical state machine, within each state, there can also be a substate, and even further, that state can have its own substate, and so on. Hierarchical state machines allow an increase in overall complexity of the machine while still providing the same benefits of a finite state machine. Only running code necessary to the current states, minimizing conditional statements, easier debugging, etc. As an example, in our current project, if Jammo is on the ground, the gravity will be different than when it's in the air. But in both, we want Jammo to be able to move around and rotate. So what we'll do is have a two-tiered hierarchical state machine. The root state will handle Jammo's gravity, and the substates will handle the transitions between the idle, walk, and run movement states. To begin, let's break down how state machines actually work. And don't worry if this all doesn't make sense at the start. Hopefully it will by the end of the video after we implement it ourselves. With state machines, we have three different concepts: context, abstract state, and concrete states. Each state that Jammo can possibly be in when the game is running will be a concrete state. As mentioned, this includes running, and we also currently have walking, idle, grounded, and jumping. These concrete states are all individual classes that derive from the same abstract state or base class. This means that they inherit the public and protected methods and variables defined from that base class. Deriving from the abstract state guarantees that all of the concrete states will have particular functions and variables, which will keep our code clean. The context is what handles the instances of concrete states. Context will pass data to the currently active concrete state, and in the case of hierarchical state machines, active states. The states then use this data to react with their specific logic. Data that is passed to the concrete states from the context will also determine when one concrete state should switch to another. Like if the jump button is pressed from the grounded state, it should switch to the jump state, and Jammo should jump. And that's about it for the concepts of a state machine. Now, let's begin the implementation. In our project, we will create a new folder in our assets titled State Machine. In this new folder, we will make a new script titled Player State Machine. And we will continue by adding the rest of the scripts we will need for this entire tutorial: player base state, player grounded state, player jump state, player idle state, player walk state, player run state, and player state factory. All of our new scripts that we just created will essentially replace our current animation and movement controller with jumping script. However, they will retain a lot of the same logic, and if the state machine works as intended, Jammo should function exactly the same. So let's remember that going forward. And looking at our blueprint of a state machine, we can map these out to their purpose. Player state machine will be considered the context. Player base state refers to the abstract state. Grounded, jump, idle, walk, and run are all concrete states, and the state factory creates the concrete states from within the context. Let's start with the context. Opening player state machine script, we know that the context will store a lot of the data that the concrete states need to perform their logic. What this means is that the player state machine script will retain all of the variables from the old animation and movement controller script. Let's go ahead and copy all of the member variables over now. It's worth noting that by keeping the variables in the context instead of within the concrete states themselves, we could technically have multiple state machines running off of the same data. In addition to the variables, we are going to want to keep a few of the functions as well. We still want the callback functions that we use to track the player's input using the new input system: on movement input, on jump, and on run. Be sure to add the namespace unityengine.inputSystem at the top of the file. And we'll need to go ahead and copy the entire awake method, which sets the callbacks, and assign some of the member variables like character controller, input system, player input, and the animator. In the awake method, we'll also see the setup jump variables function being called. Again, this function makes sense to keep within the state machine class because it's where we first assign these values that the jump state will use. So we'll copy and paste that function. Our update function will keep the character controller's call to move because it is used in all of our movement states, and same goes for handle rotation. The last we'll copy is the onEnable and onDisable methods, which are used to enable and disable the action map of our input system. Here's a quick look through our code, and if we replace our original script with our new player state machine script, in play mode, we'll see Jammo currently only able to rotate. Okay, we'll come back to the context many times as we go forward, but for now, let's move on to the abstract state, or player base state file. The purpose of the abstract state is to establish methods that all concrete states must have. This is because concrete states derive from the base state. To start, we'll remove all of the using namespaces from this file. We don't need them. Next, we'll remove monobehavior from the class declaration and add abstract after the access type. Abstract means that we cannot create an instance of this class. Remember, we only create instances of the concrete states. Next, we'll create the following methods for concrete states and go over each in detail throughout this tutorial as we use them. Enter state, update state, exit state, check switch states, and initialize substate. All of these methods will also be declared abstract, and this means that the concrete state classes will need to define the functionality themselves. Below the abstract functions, we'll also declare the remaining functions that will be locally defined later. Update states, switch state, set superstate, and set substate. And let's delete the monobehaviors update and start. In all 5 of our concrete states, we'll replace monobehavior with player base state. Immediately, an error will appear in each stating that we need to define the abstract methods from the base state. Let's write all of them as empty methods for now, but this time with the term override instead of abstract. Great! Despite not doing anything, we can now create instances of these concrete states. In our context file, we can declare a new member variable, current state, of type player base state. And thanks to Jason Story for the recommendation, we have a clean way of creating concrete states. We'll use a state factory. In our player state factory file, we'll remove the using namespaces and monobehavior. We'll declare a member variable, context, at the top of the file of type player state machine. And then we'll write what's known as a constructor by typing public player state factory that expects a parameter current context of type player state machine. A constructor function is what's called when we create a new instance of a class. So here we are saying that a new instance of a player state factory requires a player state machine to be passed in. Inside of the constructor function, we'll set the context member variable to the passed in current context argument. And now the state factory will hold a reference to our state machine. Next, we'll declare 5 new public methods, one for each of our concrete states: idle, walk, run, jump, and grounded, of type player base state. Inside of each, we'll return a new instance of their respective concrete states. For example, idle returns a new player idle state instance. Awesome! Back in our context file, let's declare another member variable titled states, of type player state factory. And in our awake method, set that equal to a new instance of player state factory passing in this. Remember, in the player state machine file, this refers to itself, which is a player state machine instance. And like we just programmed, player state factory's constructor expects a player state machine instance to be passed in. Right below that, we'll set current state equal to the invoked states grounded method, and then invoke current state's enter state method. We now have our grounded state instance set to the current state within the context. If we place a debug.log inside the enter state of the player grounded state, adding the player state machine script to Jammo and pressing play, we'll now see the statement logged. Great, we have now entered our first instance of state. Now, a big feature of state machines is switching between states. In our player base state file, we'll declare and define a method, switchState, that will accept a parameter newState of type player-based-state. SwitchState will first call exitState, which means that whatever the current state is will perform the logic defined in its exitState method. We'll then call enterState on the new state and end the method by setting the context current state to the new state. But wait, we don't currently have access to the context from within our concrete or base state. Fortunately, our player state factory makes this an easy fix. In our player state factory class, we can pass in the same context that we stored in the player state factory's constructor as an argument for each of the concrete states. We'll also pass in this as a second argument, giving each concrete state access to the factory itself. Immediately, we'll be met with an error stating that the constructors of each concrete states do not expect an argument to be passed in. So in each of the concrete states, we'll go through and add constructor functions that have a parameter current context of type player state machine and player state factory of the same type. And to take this even further, we can create a constructor function inside of the base state that does the same thing. In the base state, we'll add a protected variable titled CTX, short for context, and a protected variable factory. We'll create a constructor that expects current context and a player state factory parameter, the same as the concrete states. Then we'll set CTX equal to the current context, and we'll do the same for the factory member variable with the player state factory. Now we'll get errors in all of the concrete states again. This is because the base constructor now expects these arguments. To fix this, we'll extend each state's constructor by writing :base and pass in the arguments from the local state's constructor. What this does is pass the concrete state's arguments directly to the base state's constructor. Now in the base state, we have access to the context. This means we can try to set the context current state to the new state. But wait, another error. This time it's because the context current state is not publicly accessible. We could just add the public access type, but we also have the option to create getter and setter methods for member variables. Getters and setters are a cleaner way to access member variables of another class. They allow us to designate whether we want the accessing code to only be able to read a value by using the getter and or to change the value using the setter. The notation to declare a getter and setter is to start by writing the access type, in this case public, followed by the type of the variable, player-based state for the current state, and then a Pascal notation variable typically of the same name of the member variable, in this case current state. We then use brackets and then whichever of the getter-setter methods we want. In this case, we'll add both. We'll type get, then brackets, then return the member variable that you're trying to get. And for set, we use the member variable and set that equal to value. Now in the switchState method of the base state, where we have access to the context, we can use the setter to reassign the value. Awesome. We'll end up using getters and setters for pretty much all of our member variables that are accessed from concrete states. Doing so, make sure that we know exactly how we are using those variables. Okay, because the CTX variable is protected, that means that this variable is inherited by classes that derive from the player-based state. This means we have access to the context and state factory in each of our concrete states, and we also have a working switchState method. Let's make switchState, setSuperState, and setSubState all protected. But when should we use the switchState method? Well, remember we created the method titled checkSwitchState on each of our concrete states. So when should the grounded state switch to another state? Well, we can imagine that if the player presses jump when they are on the ground, it should switch to the player jump state. Using our knowledge of getters and setters, we can see in our player state machine that isJumpPress is updated when the player presses the jump button. So we can create a new getter for isJumpPress and access that in the grounded state. If isJumpPress is true, we'll call switchState and pass in the invoked jump method of the inherited factory. That's the beauty of having access to both the context and the factory from within the concrete states. It encapsulates the state machine logic so that we don't need to write public state-related functions inside of the context. Instead, they can be handled inside the states themselves. So what happens when we switch to the new state? From our switch state method, we know that enter state is invoked on the player jump state. If we look at our original script, we have conditions set in handle jump so that it occurs only one time when the player first presses jump and they are grounded. Well, that's the point of the grounded state. Jammo is grounded. And we know that enter state is only called one time. So we will copy the logic from within that condition and paste it inside of its own handle jump function of the player jump state. Then invoke that inside of the player jump state's enter state function. However, remember we need to access all of these variables from the context now. This means that we should make getters and setters for each variable, and then replace each variable in the logic of the player jump state with the new getter and setter. Now remember, we still need to call check switch state somewhere for its logic to actually run. As we know, update is supposed to run every frame of the game, and we definitely should check if the state should switch every frame. So in all of our concrete states, update states methods, we'll invoke the check switch states method. However, because our concrete states do not derive from mono behavior anymore, we know that the update method will not be run. This isn't the case for the context though. So we just need to invoke the current state's public update method in the player state machine's update method. Testing in play mode and pressing jump, Jammo will jump. However, as we can see, we're still missing a lot of logic, like gravity. In our original script, we had a function handle gravity that had multiple conditional statements. The first condition would be true when the character controller was grounded. That logic would start the coroutine to reset the jump count as well as apply the lower gravity amount. What's cool about state machines is now we can keep the logic about the jump tied to the jump state. We'll take that snippet related to the jump and place it inside the exit state method of the player jump state. Like before, we'll now switch the variables to getters and setters. And we'll also move the definition of the iJump reset routine into the jump class as well. Exit state is called during our switch state method, so let's also finish our check switch state implementation for the jump state. If the context character controller is grounded, we want to switch back to the grounded state. And this will call the enter state method of the grounded state. With the remainder of that original conditional logic, in the grounded state's enter state method, all we need to do is set the current and applied movement y values to the grounded gravity value from our context. What's cool is that for setters, we can target the y value of the vector 3 by declaring the type of the y value, a float. And now we can just copy and paste the remaining handle gravity logic into the player jump state, and we'll also switch the variables to getters and setters, and call it inside of update. Testing in play mode, and boom, our jump logic is working and switching back to our grounded state. The only oddity is that we can now hold jump and Jammo will continue to jump over and over again. To quickly fix this, we also now have an unnecessary variable from our previous implementation. Is jump animating? Within the jump's exit state method, we know that Jammo won't be animating because we disable that boolean with setBool. So let's rename this to require new jump press. We'll then set this to true if jump is pressed on exit of the jump state. In the context, we'll rename the member variable getter and setter. And in our onJump callback, set it to false when the jump button is pressed. Then in our grounded state's check switch state method, we'll require the jump button to be pressed and the new require new jump press bool to be false. And now our state machine is effectively switching between jumping and grounded exactly like before, but only running the logic necessary to do so. Perfect. Let's finish this up with the hierarchical aspects of the state machine implementation. Currently, Jammo can stand and jump. And while it's doing this, we want it to be able to move around. This logic will be handled in Jammo's substates. Back in our player base state file, we have the remaining methods: initialize substate, set superstate, and update states. Let's first define set substate and set superstate. Set sub will expect a parameter new substate of type player base state. and set super will expect a parameter new superstate. Set substate will set a new protected member variable current substate equal to this value, and set superstate will set a new member variable current superstate equal to its parameter as well. Set substate will then call set superstate on the new substate, passing this as its argument and therefore setting itself as the superstate of its own new substate. What this means is that anytime we call set substate, we create almost a parent-child relationship, but we also create the inverse as well, child to parent. With that in mind, we can now go to our player grounded state and player jump state to override the inherited initialized substate method. Remember, we have three possible substates: idle, walk, and run, and we want to create the correct substate from the moment both parents are constructed. In our original code, we had a method, handleAnimation, that distinctly tells us when we want to transition between each. We can use similar logic inside of the initialized substate methods. We want a substate of idle when the character is not moving and not running. We want a substate of walk when the character is moving but not running. And we want a substate of run when the character is moving and running. And as shown, we'll create the associated getters for these two member variables of the state machine. We will then call each initialized substate method in the constructor of the grounded and jump superstates so that the proper substate, idle, walk, or run, is created regardless of which superstate is active. We can then go ahead and add the proper logic in each of these three substates to switch between one another. Idle should switch to both walk and run depending on which of the movement press and run press variables are true. Walk should switch to either idle or run, and run should switch back to walk or idle. Same as before, we call check switch states in our update state method. Let's quickly finish the movement logic for each of these states before moving on. In the enter state method of each, we will access the context animator and appropriately set the isWalking and isRunning hash booleans. In idle, we'll set the applied movement x and z values to 0 in the enter state method. In walk, we'll set the applied movement x and z values to the corresponding current movement input values inside of the update function. And the same for the run state, but multiplying by a larger run multiplier. Then we'll create the appropriate getters and setters in the context. If we enter play mode right now, we'll immediately notice something. The substates aren't doing anything. That's because update is only being called in the context on the current state, but not on its substates. Let's change this invocation to update states. And back in our player base state, we'll set update states to public and give it the following definition. It will call its own update state method. Then, if it has a substate, we'll call update states on that. This will cause all substates that are a part of the superstate substate chain to be updated. And it's worth noting that we can actually do something similar for exit state with an exit states method, but we don't really need that for our current machine. And now, there are just a couple more things to fix. Entering play mode once again, we can move around. However, we can no longer jump. But why? The answer is in our switch state method. What happens when we switch state from idle to walk is that the context current state becomes the substate. We need a way to tell if a concrete state is at the top of the state hierarchy. To do this, in our player base state, we'll create a new member variable, isRootState, that will default to false. We can then use this as a condition inside of our switch state method so that we only switch the context current state if it's at the top level of the state chain. And now in our grounded and jump states, we'll set this value to true in their constructors. But what about switching states that are not root states? Well, if it's not a root state, that means that it's a substate, and therefore we have a superstate. So we'll add a second condition that checks to see if it has a superstate, and if it does, to set that superstate's substate to this new state, essentially transferring the superstate over to the next state. Okay, one final change that we'll need to make in this script, some of you may have picked up on. We've been using the private member variable notation for protected member variables in our base state. We can go ahead and switch all of these to private, and then create protected getters and setters for isRoot state, CTX, and factory. We'll then switch to these in the concrete states. And that's it. Jammo is now working exactly as it was before, but now we have the power of a hierarchical state machine that splits our previous logic into condensed states and enjoy the many benefits that come with the state machine. Awesome job! There are definitely changes that can be made here, and if you have recommendations, feel free to leave them in the comments. I love learning from this community. To vote on the next tutorial that we will cover on this channel, be sure to check out the iHeartGameDev Patreon account. And of course, the biggest thank you to all of the current supporters. You help make this channel happen. If you are interested in joining an awesome growing community, we would love to have you in the iHeartGameDev channel Discord. And of course, for updates on the next video, feel free to follow me on Twitter. But that's all for today. Thank you so much for watching, and I'll see you in the next video.